Okay. Well, first thing we need is the identity. What is the sine of 2 theta equal to?
Isn't it just 2 sine theta cosine theta?
Huh? And if you'll remember, our triangle was 8, 5, I think it was root 39.
Yep.
So the sine of 2 theta, what's the sine of theta?
5/8 or 5/8.
What's cosine of theta?
Root 39/8.
What does that give us? 5 root 39 over 32. Now, do we have to worry about the sine of the sine?
You got it over 32?
Yeah. The 2 took out, in other words, I actually had 10 over 64. 2 times 5 is 10.
Mm-hmm.
8 times 8 is 64.
Oh, okay. Yeah.
That simplifies to 5 over 32.
Mm-hmm.
Now, do we need to worry about the plus or minus sign on this? We already figured out that that's third quadrant.
Mm-hmm. I don't think you need to.
No, you don't. The only time you have to worry about it is when you have these half angles. Those half angles, you can always tell what quadrant it's in. When you have double angles, you really can't. In other words, if theta was in the latter part of the third, your double angle would be in a different spot. So this is all you need, is that formula. And, hold on a minute. Hold on a minute. Sine of theta in the third quadrant is negative.
Oh, so is the whole thing negative then?
And no, because the cosine of theta in the
that one's also negative.
It's also negative.
Because aren't sine and cosine only positive in the first part?
Yeah, we accidentally got the right answer, not intentionally. One of the few times you can make 2 mistakes in math and they make up for, they give you the right answer. So we do have to consider all of that.
Mm-hmm.
All right.
10.
10.
I don't know why I checked 10 off. I haven't done it.
That means that's what the check mark means?
I haven't done it. I don't know why I checked it off.
Okay. Well, what's the sine of 7 pi over 6?
Isn't it negative 1/2?
Good. What's cosine of 7 pi over 6?
Negative square root 3/2.
Tangent.
It's the negative 1/2 over square root of 3/2, isn't it? The square root of 3/3.
Yeah. And it's positive.
Mm-hmm.
Actually, I prefer this answer. Only because we're not concerned about irrational denominators. This is what you get if you look at the triangle that we're talking about.
Yeah.
You look at the 30-60 triangle, that's 1 square root of 3, 2. If you take the tangent of 30 degrees, you get 1 over square root of 3. And the reason you don't worry about rationalizing it is because, what if I said, what's the cotangent? Well, the cotangent of that is obviously root 3.
Right.
So rationalizing it defeats the purpose, because if I rationalize it to get that, now I say, what's the cotangent? Well, now you get 3 over root 3. You got to rationalize it again. You end up going through all these multiple rationalizations, which isn't really necessary. To be honest with you, I've never quite understood why math insists upon having rational denominators. They're not necessary. Now,
Maybe they just want to make it more difficult.
the other 3 trig functions, you have any questions about those?
I don't.
Okay. So
I don't like with this one. Yeah.
Right. In other words, cosecant of 7 pi over 6 is going to be minus 2.
Mm-hmm. And the other one's, I think it's negative 2 square root 3 over 3.
Again, I prefer
If you rationalize
not
it.
rationalizing it.
Yeah, our teacher likes us to rationalize the ones when we have to give all six angles, but not for other ones for some reason.
Fine. Go ahead and rationalize them, though. In other words, you'll find that it does create extra work. In other words, if I want to know the cotangent, it's much easier if I haven't rationalized it. It's not. If I've rationalized it, now I've got to rationalize it again. So, but whatever your teacher wants, do that. All right. Find the inverse cotangent of negative 1. So the first thing to realize is that we're looking for an angle or a number.
Like a number.
We're looking for a ratio.
Yeah.
In other words, you take trig functions of angles to get ratios. You take inverse trig functions of ratios to get angles. So we're looking for an angle there. And it's negative 1. Go ahead and use your calculator on this.
Okay. Do I just plug that in?
Well, you have an Inspire?
Mm-hmm.
Yeah. Hit the trig key. Hit
and then I go to
cotangent, the inverse cotangent, and type in negative 1.
I got 135.
Really?
Is that it? I guess that.
Well, that's correct. In other words, if you took the cotangent of 135, you would get negative 1. But when you take the inverse cotangent of negative 1, you should have gotten minus 45 degrees. Or minus pi over 4. Because most calculators, when they're talking about tangent or cotangent, they're going to give you the positive angle is going to be in the first quadrant. The negative angle is always going to be in the fourth quadrant. So the fact that they gave you the second quadrant answer is interesting. I have an Inspire. Let me see if mine does that also. That's different. And it's significantly different. And by that I mean that all calculators should give you fourth quadrant answers for this, not second quadrant answers. Hold on, I'm going to have to plug mine in. Battery has run out. Yeah, that's very puzzling as to why it would give you a second quadrant answer. Even though cotangent is negative in the second quadrant, and that is a correct answer, it's not the one that generally is given by calculators. In other words, calculators are all programmed to give you positive answers in the first quadrant, negative answers in the fourth quadrant. So I'm trying to figure out how you would ever get 135 degrees. As soon as my calculator boots up here, I can do it on mine and see what I get. A little curious here. I would expect to get minus 45 degrees. Is what I would expect. Now,
Maybe it's because it's the cast version. I don't know though.
no, mine's a cache version also. Let me see. We're taking inverse cotangent of -1. I get 135 degrees also. Now, the question is, let me do inverse tangent of not -1. Notice what I get. Do inverse tangent.
Of the same thing, inverse tangent?
Of -1. You get minus
Negative
45 degrees, right?
Mm-hmm.
Yeah, so why is that different? Now, for sure, tangent and cotangent are negative in the second quadrant. So like I said, 135 degrees is not an incorrect answer, but it's not the answer you expect. You always expect the fourth quadrant answer, and yet they gave us the second quadrant answer, which kind of spoils my entire presentation, but I'm going to do it anyway. I don't know what's going on with that calculator. It's a little weird. But if I said to you the inverse sine of 1/2, what would that equal? Don't do it on your calculator. Just I'm trying to explain something to you.
Okay. I'm not sure.
30 degrees. In other words, the sine of 30 degrees is 1/2.
Oh, yeah, that makes sense.
What if I said the inverse sine of -1/2? What do you think it's going to give you as an answer?
Let's see. Would that be in the third quadrant then?
Actually, it's always going to give you the fourth quadrant answer. So it's always going to give you this. If you're doing cosine, let's talk about cosine. If I said, what's the cosine of square root of 3/2? That's 30 degrees also, correct?
Yeah.
But if I said, what's the inverse cosine of -√3/2, it should give the second quadrant answer only. It does not give you the third quadrant answer. Go ahead and do it. Put in inverse cosine of -√3/2. It's going to tell you 150 degrees.
Uh-huh. Got 150.
It doesn't give you 210. And yet the cosine of 210 is also -√3/2. In other words, it only gives you the one quadrant. It does not give you both quadrants as an answer.
Mm-hmm.
Now, that's difficult to explain to you when your calculator's showing you something else, but when you take the inverse tangent of -1, you're going to get a fourth quadrant angle, always. You're not going to get the second quadrant answer, which happens to be 135 degrees. And yet, when you did cotangent, you did get 135 degrees. That's astounding to me. I actually think that that's a bug in your calculator. I truly do. because mathematicians have decided that inverse tangents of positive numbers are first quadrant angles, inverse tangents of negative numbers are fourth quadrant angles, not second. In other words, they could give you multiple answers if you wanted, right? In other words, both of these are correct, but they only give you one answer, and it's always the fourth quadrant one. So how you got 135 degrees, or how this calculator gives 135 degrees for that answer, I'm at a loss to explain, and I think you should talk to your teacher about it and ask him, because it shouldn't be like that.
Okay.
Okay? So let's go on. But that is the case with all inverse trig functions. They only give one quadrant. For positive angles, it's the first quadrant. For negative angles, it's either the fourth if you're talking sine or tangent, or it's the second if you're talking cosine. If you do an inverse cosine of a negative number, you're going to get the second quadrant only. They're not going to give you the third quadrant answer also. And that's important to realize. In other words, they're choosing one as the principal one. And for sine and tangent, it's first quadrant or fourth quadrant. It's only two choices you get that your calculator is going to give you. For cosine, it's first quadrant or second quadrant, whether it's positive or negative. So this doesn't make any sense as to why our calculator would give us that answer. I think the answer there is minus 45 degrees. Although, yeah,
that's weird.
That is weird. I don't understand that. Okay, let's look at the next one. Exact expression. What's tangent of 60 degrees?
Oh, let's see. So it's root 2 over 2 over root 2 over 2.
Oh, that's 45 degrees.
Okay, so then it's...
You really need to memorize these two triangles.
I'd get a lot better if I write a circle down first.
Okay, whatever it takes.
Yeah.
And I know that I don't use the same. Your school uses square root of 2, square root of 2, and 2. Same multiples. But if you know these two triangles, you will be able to figure out all of your common angles. So what's the tangent of 60 degrees?
A second.
Looking at my triangles.
1 over root 3.
Oh, the tangent of 60.
Isn't it? Oh, of 60. Okay, so then it's root 3 over 1.
Okay, now what's that squared?
3.
What's the sine of 90 degrees?
Is it opposite? Okay, so it's 90 degrees in the first one? Just 2 over the 1?
Sine of 90 degrees is 1. In other words, in addition to these two triangles won't give you your quadrangle. They just don't. Okay? If you want your quadrangles, you either have to memorize that curve, or you have to kind of remember your unit circle and remember these 4 points right there. And that will also give you your quadrangles. You know what I mean by quadrangle? That's 90, 180, 270, 340, all multiples of 90. Okay? Or you can memorize the sine curve, and there's pi over 2, or 90 degrees. So it's 1. That's how I got the 1.
Okay.
Okay?
There it is. I was looking for a circle too.
Two triangles and the sine curve and the cosine curve, you'd be well served to just memorize them. So you can draw them from memory.
I I know the first quadrant, or the first quadrant of the unit circle.
Yeah, the first quadrant,
That's really all you need.
those two triangles right there. Those are the only two you need for first quadrant angles. But these don't help with 90-degree angles or 180-degree angles. So you have to figure out a different way to figure those out. Remember your unit circle. The first, if I have a point right there on my unit circle, well, the x-coordinate is the cosine of theta. The y-coordinate is the sine of theta.
That's kind of what I do.
Okay.
And then for sine of 90 degrees,
if I'm
the y.
looking for 90 degrees, the coordinates on that point are 0, 1. So that tells me the cosine of 90 degrees is 0. The sine of 90 degrees is 1. I go over to here. I get minus 1, 0. Cosine of 180 degrees is minus 1. Sine of 180 degrees is 0.
Yeah.
So that's the way, this is the best way to figure out your quadrangles. But this curve is so important that you know that I can't imagine you can really get through trig without knowing how to draw a sine curve. Starts at 0, goes up to 1, goes down through 0, goes down to minus 1, comes back to 0. That right there, you need to be able to draw a sine curve and a cosine curve. Because when you can do that, you can answer a lot of these questions a lot easier. All right. So the complementary angle theorem, number 13. Says the following. Here's the complementary angle theorem. Right there. In other words, every cofunction, and by cofunction I mean take the function and stick the word CO in front of it. That's how you get cosine. You start with sine and you stick the word CO in front of it and you end up with cosine. That makes them cofunctions. And it's also true that this is true. All cofunctions share this property. And cofunctions are secant and cosecant, tangent and cotangent. These are all your cofunctions. They all have this property. The secant of theta equals the cosecant of 90 degrees minus theta, and vice versa. Tangent of theta equals cotangent of 90 degrees minus theta, and vice versa. So that's our complementary angle theorem. And now let's see if we can apply it here. 1 over sine squared of 15 degrees. Well, that's the same as 1 over cosine squared of 75 degrees, which is the secant squared of 75. Now we have minus the tangent squared of 75. And there's a trig identity regarding secants and tangents. If you remember, tangent squared of theta plus 1 equals secant squared. So secant minus tangent equals what?
Just 0.
Take that formula, move
isn't tangent? Oh, isn't it just negative
side? Subtract it. So secant squared minus tangent squared has to equal 1. It doesn't matter the angle. It doesn't matter if it's 75 or 175. If these two numbers are the same, then secant squared minus tangent squared is equal to 1 by this identity right there. Always.
Is it Positive or negative?
Subtract tangent squared from both sides.
Okay.
Now you got secant squared minus tangent squared equals plus 1. Okay? Scroll down a little bit on this. You understand that last one, Sam? I kind of felt like you.
With the complementary angle theorem?
Yeah. I mean,
Yeah, I get it.
you understand why secant squared minus tangent squared is equal to 1?
Yeah, I do.
Okay. And like I said, as long as it's 75 degrees or 17 degrees or 12 degrees, doesn't matter. Secant squared of theta minus tangent squared of theta is always equal to plus 1. Does not matter what theta is. In the same way that the cosine squared of theta plus sine squared of theta is equal to plus 1. Always, no matter what theta is. All right. 14. There's a line through that. Does that mean anything?
No, it doesn't.
Okay.
That was just me writing something on the side.
Okay. I love these kind of verifying problems.
No, I don't.
I know. Everybody hates them. But they really serve one purpose and one purpose only. First of all, you're never going to find a real life problem that is like this. There are no real life problems where you have to verify that. There's only one purpose in this drill. And that is to get you to learn your trig identities. Seriously. The only purpose in verifying trig identities. Now, there are going to be trig equations that you have to solve in real life. You can come across a problem that's going to present you with a trig equation and you'd have to solve it. But never, ever will you have to verify an identity in real life. There's no purpose. You never come across a problem like that. The only purpose is in checking your identity. So when you do these problems, you take the more complicated side, which is the left side, and you start trying to figure out how can I turn the left side into the right side. Well, I see a cosine, a sine, a sine, a cosine. These are cosecant and secant. Let's start by turning everything into sines and cosines. That's generally not a bad strategy when you're trying to verify identities. If you can turn them into sines and cosines, that'll almost always work. It's not always the best way to do it, but it always works. So cosecant is 1 over sine minus secant, which is 1 over cosine. And I am multiplying that whole thing by sine x cosine x. Well, let's do it one at a time. In other words, let's distribute that to both terms. If I multiply that by that, what do I get?
Just sine times cosine.
Sines cross out. End up with cosine.
Yeah.
Now multiply that by that. The cosines cross out, and you end up with sine.
So it's 1 minus sine over...
No, it's not 1 minus.
Or not 1 minus, cosine. I wrote cosine down.
Cosine x minus sine x. In other words, that's exactly what we were trying to prove. It only took 2 steps. I had to substitute the reciprocal identity and then just multiply. That's all I had to do. Now, these verifies can get a whole lot more complicated than this. But remember that if you're trying to do a verify, then if you're already looking at a bunch of sines and cosines, convert everything else to sines and cosines and let nature take its course. In other words, that'll be your solution. If it's a different kind of identity, then that's not the correct way to go. In other words, if I get something that looks like this, I don't see any sines and cosines. So I don't want to convert these to sines and cosines. I only do that is if I already see a bunch of sines and cosines in that formula. And like I said, I see one there, I see one there, I see one there, I see one there. To prove this, just turn that into sine and turn that into cosine. And that almost always works. Like I said, it's not always the best way to do it. Like this one. Let's do this one. Cotangent minus tangent. How is that equal to 2 cotangent of 2 theta? Wow. Well, even this one, if I turn it into sines and cosines, let's say I can't, yeah, I can do that. Let's do it. Cotangent is what?
What is it? Cotangent.
In terms of sine and cosine. In other words, I'm going to turn every term into sine and cosine.
So that's just cosine over sine.
Minus sine over cosine. And they're saying it's equal to that. Well, let's do the math. What's the common denominator?
Cosine times sine.
Sine, cosine. And the top left would be cosine squared, minus sine squared. Well, what's that equal
to? Isn't that 1?
Actually, that is the cosine of 2 theta. That's one of the identities for the cosine of 2 theta.
Oh, never mind. It's sine squared theta plus cosine squared theta. That's 1.
That's 1. Exactly.
Yeah, minus is cosine 2
theta. Yeah, now I still got this denominator I got to worry about. How are we going to do this?
And it's also 2 cotangent 2 theta for the other one.
Well, that's what we're trying to prove, that it's equal to 2 cotangent of 2 theta. And a lot of these verifying problems, boy, if you get off on the wrong start, you can go for 20 minutes and not get to your answer. And sometimes you have to kind of start from scratch and you realize you're not getting there. Well, I'm getting there a little bit because I got cosine of 2 theta and we're looking for cotangent of 2 theta. Unfortunately, cotangent, What's another identity for cosine of 2 theta?
2 cosine squared theta minus 1. Or 1 minus 2 sine squared theta.
So if I try that one, if I try 1 minus 2, is it 1 minus 2 sine?
1 minus 2 sine squared theta.
And I put that in place of cosine 2 theta, and I leave my sine theta, cosine theta in the bottom. Wow. That doesn't help either.
Oh, sine, I don't know.
I don't either. Let me think about this for a second. I love these problems. They're my favorite trig problems, the verifying. It's just they can be a little tricky. I'm thinking of if there's another way to do this. Let's see, that would also be tangent, no, 1 over tangent of theta minus 1 over cotangent of theta, which becomes tangent theta cotangent theta. So we end up with cotangent theta minus tangent theta. So we could do it this way. That doesn't seem to help much. Two over cotangent 2 theta is the same as 2 over tangent of 2 theta. So that's what we're trying to prove. How do we get from this to this?
Wait, actually, never mind. It doesn't make sense. Well, the tangent of 2 theta, that's 2 tangent theta over 1 minus tangent squared theta. I know that. I don't know if that would really help, though.
What was that you just said?
Tangent 2 theta is equal to 2 tangent theta all over 1 minus tangent squared theta.
Oh, because it's, yeah, you're right. That is equal to that. And that's going to be the way to get this solution. Because 1 minus tangent squared theta is...
Oh, that's equal to...
No, it's not equal to secant squared.
It's not?
No, it's tangent squared plus 1.
Oh, plus 1.
Secant squared. So I don't know what 1 minus tangent...
If you multiply it to get to the top, no, it would still be minus.
Yeah. However, I think you're on the right track. I think that's the way we're going to have to prove it. Because cotangent minus tangent. Tell you what, let's come back to this. I don't want to waste all your time trying to prove an identity. These things can be vicious sometimes. Just if you get off on the wrong foot, you stay on the wrong foot. But the fact that we're trying to prove that leads me to believe that your tangent of 2 theta is an important identity. And in fact, that's got to be the answer. Your tangent, here, tell me, the tangent of 2 theta is 2 tangent theta over 1 minus
tangent squared theta.
Tangent squared theta. So the cotangent of 2 theta would be the reciprocal. It would be 1 minus tangent squared
theta all over 2
tangent theta. So this is what we're trying to prove the left side is equal.
Could you cancel one of the tangents out?
Well, I think we can get this right here. Let's see. If I do cotangent of theta, that's 1 over tan minus tan. Here we go. That gives you this right there.
It does?
Close. Hold on. Let's start from the beginning. I know I can do this now. In other words, once you find the right direction, okay, so we're going to start with the left only. The left is 1 over tangent theta minus tangent theta. Well, what is that? That is 1 over tangent theta minus tangent squared theta over tangent theta, right?
If you do what again?
I'm working only with the left side. So I've turned the cotangent of theta into 1 over tangent.
1 over tangent.
Minus tangent of theta. Now I find a common denominator, which is tangent of
Which
theta.
tangent? So you have 1 minus...
Now you get 1 minus tan squared theta over tan theta.
How do you get the 2, though?
Now, good question. Yeah, how is that equal to that? Well, I was certain that would be the direction for our solution. Now I can't see it because that doesn't have an identity. The identity is 1 plus tan squared theta. What if I took tan squared theta plus 1 equals secant squared, and I subtract 2 tan squared from each side, then I end up with 1 minus tan squared equals secant squared minus tan squared minus 2 tan squared. I don't know.
Yeah, if I plug in my calculator, it gets all confused, trying to tell me whether or not it's true or false.
You can't really use a calculator on these problems. You just can't. At least not that I know of how to do it. The purpose of these verifying problems is to teach you your identities. That's the only purpose.
Just to see if it was true or false, though.
Oh, well, I've never seen a teacher give a false one. If you
I know. I'm just saying that.
False ones, you got torturers for teachers. Seriously. And in fact, the hardest problem one can ask on a trig test is a multiple choice verify question.
Oh, that's what.
Much harder than a regular verify question. In other words, as long as I know that that's an identity, then all I got to do is manipulate one side to make it look like the other. But if you give me 5 choices, now I don't know that. I got to disprove 4 of those choices. And disproving identities is a whole lot harder than proving them. So, like I said, I've never seen a verified identity that isn't true. I had a student give me one night. I worked a half an hour on it, couldn't solve it, and came to the conclusion she'd given me a typo. Because, like I said, if you want math torture, just give somebody an identity that's not an identity. And they'll spend all day trying to prove it, and it's not an identity, so you can't prove it.
So it should be true.
So the right side here is 2 over tan of 2 theta. Let's
Is that it?
The right side. I think that gets it, because now we get.
And you get 2
theta was the tan of 2 theta all over 1 minus tan squared of theta, right?
Wait, what? What did you do?
In other words, that identity.
Did you just multiply it up to the top? Wait.
I took the right side and started working with it.
You made it to the 2 over tangent 2 theta.
Yeah, and then that turns into this, and that turns into 2 times.
Wait, didn't you
1 minus tan squared theta all over tan of 2 theta.
Did you expand the Did you expand the tangent 2 theta on the first part to
I went from the right side to this.
Yeah, on the right side. And did you make that into the bottom bit?
Well, I made the tan of 2 theta into the denominator.
Except wouldn't it be 2 tangent theta all over 1 minus tangent squared theta?
2 tangent theta over 1 minus tangent squared theta.
Yeah.
Okay. So it's 2 tangent of theta, like that. And now the 2's cancel. And I end up with 1 minus tan squared of theta over tan squared, or tan of theta, and that's what that is.
Wait.
So I can verify it. I can prove it.
Where'd you go from that second step? From the 2 over 2 tangent theta?
Well, these can be a little tricky. Let me erase everything here. Let's start with the right side only.
All right.
Okay.
Let me just erase this.
So that becomes, and there's nothing illegal or improper about doing the right side.
Mm-hmm.
Okay, so that's 2 over tan of 2 theta, correct?
2 over tangent, yeah.
Those two are equal. And now I know that the tangent of 2 theta is 2 tan of theta over 1 minus tan squared of theta. With me?
Uh-huh.
Now invert and multiply. So that gives you 2 times 1 minus tan squared of theta over,
so you're putting the
2 tan theta. 2's cancel. So this is what the right side is equal to.
So you're just putting the 1 minus tangent squared theta on top and multiplying it all by 2?
Okay, I went from this step to the next step by reciprocating the denominator and multiplying.
Mm-hmm.
That's the way you divide by fractions.
Yeah.
And that's all I did. So when I reciprocated this denominator and multiplied, I got that.
Mm-hmm.
2's cancel. I get 1 minus tan squared of theta all over tan of theta. And that's what that's equal to.
1 minus tan squared theta all over tan theta.
Cotangent of theta is 1 over tan theta.
Uh-huh.
Minus tan theta. Well, add those two or subtract those two fractions and you get this.
Okay.
That's equal to that. So when you find a problem like this, where I can solve it if I work from the right first, there's nothing wrong with doing that. And once you figure out how to do it, now you can go backwards. In other words, now I can turn the left. This is the left right here.
Yeah.
I can just work backwards and get it to equal that.
Okay.
So even if the teacher says you can only work with the left side, it still works. Even if you work with the right side, you'll be able to figure out how to do it. Okay. And as far as I know, there's no rule that says you can't work with the right side. It's just most of these problems, you work with the left side or you work with the side that's more complicated looking. But in this problem, I'm not sure that's the left side. The right side might actually be a little more complicated because it's got a cotangent of 2 theta in there. Mm-hmm. So there's nothing wrong with turning the right side into the left side.
Mm-hmm. So the reason you made the 2 cotangent 2 theta into the, where is it?
Made it into
2 over tangent 2 theta is just because cotangent theta is 1 over tangent theta. So you just kept the 2.
Yep.
Okay, that makes sense.
In other words, tangent of 2 theta is the same as 1 over cotangent of 2 theta. Or vice versa, cotangent of 2 theta is 1 over tangent of 2 theta.
So you're just keeping, I mean, I guess you could,
Yeah, as long
say
as that's the same,
like there's an imaginary 1 in front of the tangent.
It doesn't matter if it's 2 theta or 210 theta. Tangent of 210 theta is the same as 1 over cotangent of 210 theta.
And I guess you keep the 1 there. You could say there's like an imaginary 1 in front of the tangent, I guess.
You don't even need that. In other words, that is 2.
That makes sense.
Because of that 2 right there.
Yeah.
And then now you go from there.
The 2 there, so you'd have to divide. Okay.
Yeah, I'm sorry. I confused you by putting there. What we're doing is cotangent of 2 theta equals 1 over tangent of 2 theta. And now I use my tangent of 2 theta identity, and that produces the answer.
Yeah.
All right. Okay. The next one. How are we going to do that?
I am not sure. Is this just the sine and cosine graphs?
Solve graphically. Well, we could certainly solve it algebraically in your calculator. That's the inverse cotangent of 3 equals theta. You can get that number out of your calculator. But it says solve it graphically. So to solve it graphically, what you want to do is go in and plot 2 things. The first function is cotangent of theta. The second function is 3. Wherever those 2 cross, that's your answer. Now, cotangent of theta looks like this. Goes between 0 and pi. Okay? Now, y equal 3 looks like that. So that's your solution right there, where they cross. And that's what they want you to do when they say solve it graphically. So they want you to graph cotangent of theta. They want you to graph y equal 3. And wherever the 2 cross, that's a solution. Now, cotangent of theta is periodic, like all trig functions. So it has another cycle there. So actually, I have another answer there. And I have another answer there. And I have another answer there. So there are a lot of answers. Now, if they tell you the answer has to be between 0 and pi, then this one is the answer. But whenever they tell you to solve something graphically, especially a problem like that, just make that y sub 1, that y sub 2. It'll graph both curves. Where they cross is the answer.
Okay.
And you could do that on a TI-84 or the Inspire. The Inspire also lets you put 2 functions in. Your first function is cotangent theta. Your second function is y equal 3, or f of x equal 3. But it's their intersection that's important. And according to this question, I'm guessing that any answer would work as long as it's where they cross. In other words, they don't specify that it has to be between 0 and pi, or pi and 2 pi, or whatever. So you're going to have multiple answers, but the one that's between 0 and pi is probably the one they're looking for. All right, let's real quickly, we're almost out of time. Let me just show you how to do the next one.
Okay.
Not as hard as it looks. The factoring problem. Got 2 things multiplied together equals 0. Each one of them is 0. So sine of theta equals 0, and sine of theta equals 1. are your two answers. Well, that occurs for all solutions. Well, that occurs at 0 plus, use K or N?
K.
So that's the answer for that one.
So just 0. I guess that'd be 0 plus K pi. Yeah.
Yeah, that's what I prefer, but I was doing everything in degrees. The answer to where sine of theta equals 1 is pi over 2
Pi over 2.
plus K times 2 pi.
Okay.
So those are your answers right there, both of them. But whenever you're solving trig equations like this, think factoring. It's almost always, it's either a factoring problem or it could even be a quadratic. If I had this, that's just a quadratic function. It's going to factor into sine minus 2 times sine plus 1. That solution doesn't work because sine can never be greater than 1. So the only solution to this problem is sine equals negative 1. But think polynomials when you see these kind of equations, meaning your solution lies in factoring or factoring the quadratic or whatever.
Okay.
Did we cover everything?
Yeah, we did.
Okay, good. Your test is tomorrow or next Thursday or tomorrow?
Tomorrow.
Tomorrow. Okay. Well, good luck on it.
Thank you.
All right, Sam. You have this might be the last time I talk to you since you're taking your final, but do you know where you're going to college?
No. Well, we still have probably another test after this. It's just the seniors are graduating, so.
Okay. Well,
we have to take the finals now.
if you go to college, I'm available. You're going to end up taking calculus, I'm sure.
Probably.
So don't forget me.
Thank you.
All right, Sam. Good luck.
You too.
Talk to you later. Bye-bye.
Bye.
Wow, you just